When we point our telescopes at the night sky and zoom out, we find a universe densely packed with light, clustered into glowing webs of galaxies that stretch across the dark. This spherical boundary represents our observable universe, extending 46.5 billion light-years in every direction. It contains an estimated 2 trillion individual galaxies. We currently live in a golden age for observation. Using instruments like the Hubble Space Telescope, we can still detect the fading microwave glow left over from the Big Bang, giving us a clear view of the universe's earliest history. But that view is temporary. The space between these galaxies is stretching, and the rate of that expansion is actively speeding up. Dark energy, which makes up roughly 68% of the cosmos, drives this acceleration. It is a constant outward pressure pushing the fabric of space apart. Because this expansion is accelerating, the universe acts as a slow eraser. It is steadily moving the visual evidence of its past beyond our ability to see it. We can map the spatial limits of our reality using 2 distinct boundaries. The first is the reachable limit, which ends 16 billion light-years away. Even if we traveled at the speed of light, we could never reach a galaxy beyond this point. The space between us and those distant targets is stretching so quickly that a light-speed trajectory can no longer close the gap. The second boundary is the future visibility limit, resting at a radius of 62 billion light-years. This is a hard physical wall for information. Any photon emitted today by a galaxy beyond that limit will never reach Earth. The underlying expansion simply pushes the light backward. Our universe is defined by mathematical borders. The physics of cosmic expansion outpaces the speed of light, creating a reach that is strictly finite. If these galaxies still exist, how do they actually disappear from our telescopes? The mechanism is called redshift. As light travels through expanding space, the expansion physically stretches the light waves, lengthening their frequency. This stretching shifts the light along the spectrum, from visible blue to red, then down into invisible infrared, microwaves, and finally radio waves. Receding galaxies appear to freeze in time, growing redder and fainter until they slip past our ability to detect them. Expansion erases the signals we need to observe these distant objects. They continue to form stars in the dark, but the data required for the human eye to see them is permanently lost. If we look trillions of years into the future, we see the final result. The star fields slowly wink out, leaving an overwhelming, pitch-black void. Eventually, every galaxy outside our local cluster will cross the visibility horizon and fade into blackness. Astronomers in this distant era will point their telescopes outward and see absolutely nothing. The cosmic microwave background will be too faint to detect, and there will be no receding galaxies to prove the universe is expanding. Future scientists will likely conclude that their isolated cluster of stars is the entire universe. They will lose the foundational evidence that led astronomers like Edwin Hubble to realize the cosmos is growing. Humanity occupies a specific window in time. We arrived late enough for life to evolve, but early enough to witness the universe's history before the lights go out forever.